Welcome to another video of the CompTIA Network Plus N10 This is Chapter 7, Routing. So the objectives we have on the board today is 1.1, compare and contrast the Open Systems Interconnection or OSI model layers and encapsulation concepts. 1.4, given a scenario, configure a subnet and use appropriate IP addressing schemes. 2.1, compare and contrast various devices, their features, and their appropriate placement on the network. 2.2, compare and contrast routing technologies and bandwidth management concepts. 5.2, given a scenario, troubleshoot common cable connectivity issues at select appropriate tools. That's supposed to be and, oops. Okay, so what do you see in this picture? What are these devices? Well, these are routers and they do many different things. If we take a look at the labels on this rack here, we'll see that one is WAN, or you should know now that is wide area network. One is for the LAN or local area network. But then what's this over here? We have LTE. Nowadays I see corporate environments with maybe 5G backups or some sort of device they're plugging into or a hotspot. So meaning that if the WAN fails, then it will carry over to some sort of backup circuit, maybe a second provider or even cellular data nowadays. And here is the more friendly home version that you may know. Maybe you have something like this at home or in a small office that's not quite as large as this and won't take up as much room. Okay, so I want you to think about what you just saw in the last picture, especially looking at the small little router that you might have at home. So let's talk about that and how that works. So is it really a router or is it a switch? Well, it had exactly the same layout here. It had one of these and four of these. So it can intake an uplink and it can route, and then it can also provide a local area network for different computers to talk to each other, as well as also access a WAN and a LAN. So you're getting both in one. So you don't need to separately buy a switch. If you have a router nowadays, they come together, and they can also have other features like a firewall or maybe some sort of hosting or server, or it's getting more complex these days. Okay, but today we are particularly talking about routing. How does one packet go from this computer to this computer, especially outside of its LAN? How does it travel across the world over the WAN? How does a router know where to send encapsulated data back and forth? So incoming data is stripped at layer 2. It verifies the destination IP address and sends it to the correct route and port according to the table. So it'll always go through here and find which route it needs to take. So that's a pretty normal routing table. Okay, let's look at to the right over here and let's look at the queue. So these are about to come in and they need to route and go out. So let's look at the very first one here. So 276.34.12. Do we see that anywhere on our table or something that looks similar? Well, yeah, this looks pretty similar. Our default gateway here is 4.1. So do we see that network ID of 0? Yep, we see it right here. So then that means on this block, it's available, it's possible to have that address host. Yeah, that would work. So that's a .12. So yeah, it's possible for you to have a 4.12 and it would route it out that way. Okay, and then you can kind of see how that goes and look at the different to's and froms and figure out where exactly is that going. Is it over the WAN? Is it over the LAN? And it'll tell you which interface it goes through. Okay. So we're going to look at more specifics. That's a more general picture of what it is, but let's get into more nitty-gritty detail. Let's look at this particular route and what it needs from the table. Okay, so the particular route we have is 10, 12, 14, 0, and it needs to find, I'm the route this packet needs. Good. Okay, so let's talk about the different terminology and different words on the table there. So destination is the to address. There's only on the gateway that connects to the WAN is set to default. There will always be a default route or a default port, a default GEN mask or a default subnet mask that tells the host if it's local or remote. Okay, common flags are H for host, U for up, or G for gateway. So there's all kinds of different flags that you'll see, and depending on what kind of equipment you're using, you'll see them on different tables as well. Okay, metric is set to 0 by default. So if you need to change the priority or how valued a route is, then you can set that. Okay, next, type or interface, or some people say iFace, is the name of the port. So very common in Linux that you would see something like Ethernet 0. Yeah, it always starts with a 0, right? Bridge 0, so on and so forth. I've even seen on some equipment like a gig for gigabit, exactly. So gigabit and then the number of the port 0 over 0 or 0 over 1. So it's a little funny with the numbers, but once you start administering some sort of routing table or some equipment, it's fine. Okay, imagine you are a packet. What would you see if you were a packet? It would look like this. It's almost as if like a directory of where you're going, right? So inside the router, you've got the routing table. You have different ports of where these routes could go out of, and those connect to different networks. We have a 10, 12, 14, 0 over a CIDR 24, and here we have a 76, 30, 40 over CIDR 24. So you can visualize it this way. So visualize that a single router could route to two different addresses. We can picture these two networks separate this way. And here's a good example of two Class A networks. Okay, next. I had a hard time kind of visualizing and understanding the subnet mask part of this. Like, I didn't quite understand. Why does this entry down here use all of these available hosts? And I was like, that's just wrong, right? Like, what does that mean exactly? Well, that's just a very lazy way of saying, hey, I want all addresses from all of these pools to be able to route to this way. So it doesn't matter if this is a 1, a 2, a 3, a 9, or a 254. It doesn't matter. It'll reply and it'll route that way. So that was a pretty fun way of understanding at least this network mask part. So if you see this, that's a royal flush. That's going to route everything out to that interface. Yeah, so that's a funny one. Okay, and I was just trying to ping all the numbers and like, yeah, they all ping. It's pretty cool. And I did like a trace route. Yeah, it's just like 1 millisecond. And yeah, it's just interesting to see that on a routing table. So you can type in Windows, show route, and you can look at the routing table you have. Okay, so this is called a loop back. It's a little plug there. That's just for testing the virtual adapter that you have in Windows. So it'll take any of those 127.0.0 dot whatever, it doesn't matter, and it'll reply because the routing table tells it to. Okay, so we just talked about the loopback. Let me get my pen. I already went over that a bit, right? So here's a pretty typical routing table you would see. So you can type show route in a command prompt and you would see something like this. So let's talk about each field. So here we have our destination address. We have our network mask. We have gateway. We have the interface. And we have the metric. So it's pretty self-explanatory what destination is. We saw an example of how to use the royal flush in the network mask. So that's pretty cool. Okay, gateway is, well, that's your gateway address. So there will be some sort of default that looks like that, and it'll be set to your gateway. So that'll pass everything through there. Okay, interface tells it what interface to go out of. You can specify the interface that you want. And then also the metric, or how important the route is or how prioritized it is. Okay, let's talk about metric because that can be explained in different ways, and different routing protocols and technologies will use metrics and distance vectors and all kinds of things like that. Okay, so let's look at an example of metrics more. Here is a router directing traffic, and it says, hey, this route is the first route on the table and has a metric value of 1. So that means it's a great route to take. It doesn't take too long, not much latency. That's preferred, right? However, route 2, metric is 10. That's way too slow. Nobody is using that. But routers are intelligent. They self-update and they know how to communicate to one another and choose the best path and make intelligent decisions on how to route. So let's say that route 1 blew up. It's no longer available. There's some sort of problem with the internet service provider or the equipment or some cables. Who knows? All kinds of things can go wrong. Okay, so then router says, well, this is the route you need to take. Even though it's slower, you'll get there because this one doesn't work at all. Okay, let's go over each line by line, and we'll talk about it. So here is the routing table we were looking at, and we'll go over which line means what. Okay, so this is called the default route, or the gateway entry. So every routing table will have some sort of default path that it has to go down. So this tells me that any destination address on any subnet mask using this gateway and using this should use this interface, and it has a metric value 25. Okay, so that was our default. Next, let's look at our loopback. Well, we already looked at the loopback a bit, and we looked at what I call the royal flush, and it has all those addresses in there. So, yep, you can target every address available, or you can do one particular address like that. Okay, and here you have metric of 300, so a pretty weird number. Not sure why it's so much higher. Okay, next one. So here we have ending in .0. That's also called our network ID. So knowing what your network ID is will let you know how many hosts are available. So since this block is 0, that means that there could be a possibility of 253 total hosts on this network, because you can't have 0 and you can't have 255. Those are reserved for the network ID and for the broadcast. So those two are stolen, so you only have 253 available addresses. Okay, and it tells you that it is not the gateway, but it's on the on link. It tells you your interface and your metric. Okay, moving on. This one is a bit funny, huh? Okay, host 201 routes to where? Where is it going? So if you try to maybe communicate with this network address, it'll just send you to, yeah, the loopback. Well, that's funny. It's almost as if it was an error or something is wrong. So as a network technician, you may see funny things like this and need to correct them. Okay, and that tells me that all available on this broadcast goes to this interface. Okay, interesting, a broadcast one. Okay, another one. We have 224 as our network ID, subnet mask. This one goes to interface, and this one goes to that other host we saw, that was 201. So if you want, you can have customized addresses going to different routes. Anything's possible. Okay, these are broadcasts. So this is normal to see on a routing table. So 255, 255, 255, 255. So all available, the very last address available, are broadcasting this interface. And this one is broadcasting this interface. So that is reserved in how they discover each other. Okay, next. Okay, let's talk about network address translation, or how you can use a device as a gateway, and this one can also become a gateway, and then this one's a gateway, like, right? And then like the next available address in the pool. Okay, we have 1241. Here we have 123137, and now this is 138. That, imagine if that was a router, or if that was a router, or if that was a router. You could just keep repeating that process and get more addresses that way. Anyway, those are all how you go down the block of IP address in the scope, right? Okay. Okay, so now you have your IP address. Let's talk about ports, or port translation. So we just talked about network address translation and how we go down the block and get more addresses that are available. What about ports? How does an application on the other side of the world talk to my computer and know like what kind of data they need and how do they communicate? Okay, so let's take this picture here. We've got a normal network that you would see at home, a 192 address. Okay, we have our local area network. Here we've got some sort of WAN address, it looks like, connecting to another WAN and some sort of computer over here on the other side of the world. So how are they going to talk to each other through a port or through an application? Okay, stay tuned. So we've got this computer, 207, and it wants to send data to the other side of the world that we saw earlier. So we can't send the data outside of the network address translation. It needs to have a specific source IP, and we need a port number to mark down and to send it where to go. So this is ending in port 80. Okay, port 80. So if we know port 80, that's a web site, like web server, web traffic, right? Down here. Okay, and they're trying to talk over port 7000. Once it gets updated, it gets a different port of 7500. Okay, now it knows web server over port 7500. Hey, I know you need this info, and I'm going to send it back to you. This is what a port address translation table would look like. Okay, so we have like different hosts. We have these really high numbers up on the ports, thousands, beyond thousands, right? And then it has to translate that information. Where is it going? And it also updates the port and changes it as well. I guess to keep us secure. It doesn't really matter, it just needs to arrive at the correct address. Okay, so in order for a web server to talk to a computer that's not inside its private network, you need to open a port. Port forwarding allows computers to talk inside your network. Like we just saw, the web server was talking to a computer on like the other side of the world. This is how you would do it. You would take that port number that you want open. Let's say, for example, here, that web server is like 150.150 would be that host. Let's say that I want to run the port 8080, right? And here, when you hit that website, you could see that port number. Although 5000 is not in this list, if it was 8080, then there you go. That's what it would look like. So this is why these higher port numbers are more important. And when they do port address translation and they go back and forth, and now you're port forwarding through your firewall and you're allowing specific types of traffic to come inside your network, quite dangerous, but for web servers and for things that are more secure in different environments. Okay. Address translation rules. You can change how you want it to be. You can have static rules. You can have dynamic rules that are changing. You can have access control lists of who can do what. So there's a lot of settings that you can change and allow these routings to go inside private networks, go out to the web, back, and you can control who it talks to when it normally shouldn't be that way, when you should be segmented from the internet and protected by your firewall and your router. You can open it up and allow anyone to come in. Okay, so we talked about routes and how routing has different priority and metrics, right? We saw the metric table. Can a certain routing technology talk to another routing technology even though they are not the same? The answer is yes. Yes, it can, and that's called dynamic routing. So let's look at each of these and talk about them a bit. So a hop count is how many hops it takes to go from this place to this place, from A to B. So the more hops it takes, the further it is, and that's not a good thing usually. It also can be referred to as distance vector. Bandwidth. Okay, most of you know bandwidth, how fast or what interface can go. Okay, another one to consider is delay, or how slow something is. You don't want a whole lot of latency or something to slow you down too much. Okay, cost. Some routing protocols use cost to determine how valuable something is. So something that's quicker, has less hops, has less delays, it's gonna be better and have less costs, right? Okay, so there are different costs for taking different routes. Let's look at the cost to route from network X to Y and vice versa. What do you see on the table? Well, if we go from A to B, that's 1, and then ABC, that's 3, ABCD. So there's different routes that we can take. We don't have to necessarily go from A to C to D because that's slower, and that's not a good way to go. There are different routing technologies that will consider different routes for different reasons. Here's an example of routers intelligently updating their tables and calculating the costs of routing. In case where the router discovers multiple routes to the same network ID, the distance vector routing protocol deletes all but the route with the lowest metric. Here's the updated table with the preferred route containing the lowest costs possible. The cost of 11 is too high, so the routing tables will take the lowest costs instead. Just as routers B and C only kept the routes with the lowest metrics, routers A and D keep only the lowest metric routes to the networks. Okay, let's talk about RIP, or Routing Information Protocol. This is a very old technology that's been around for a long time. The first version dates from the 1980s, but some say it's been there before that. But let's talk about RIP version 2. It was adopted in 1994 and is the current version of RIP. It works the same way as RIP version 1, but fixes many of the problems. RIP version 2 supports VLSM. It includes built-in authentication, swaps broadcasting for multicast, and increases the time between updates from 30 seconds to 90 seconds, which changed a lot of headaches. Okay, let's talk about autonomous systems, or they call them AS. An AS is one or more networks that share a unified policy regarding how they exchange traffic with other autonomous systems. The internet uses a single protocol for AS to AS communication. The Border Gateway Protocol, or BGP. BGP is the glue of the internet, connecting all the autonomous systems around the world. So we can see how this autonomous system uses BGP and talks to this autonomous system. It's kind of like from here to there, or there to there. So these are very large networks that connect to each other using Border Gateway Protocol. If we run the command, we can see the ID you have for BGP, and then it has a number here. There's specific amount of data that they have. I think some 16-bit address. Okay, why not simply announce and forward individual route changes as they appear? That is the basic idea of link state dynamic routing protocol. There are only two link state dynamic routing protocols, OSFP and ISIS. Okay, let's talk about open shortest path first. So open shortest path first is the most commonly used IGP, inner gateway protocol, in the world. Most large enterprises use OSPF on their internal networks. Even an AS, while still using BGP on its edge routers, will use OSPF internally because OSPF was designed from the ground up to work with a single autonomous system. Okay, I mentioned ISIS earlier. From a neighborship through the hello packets, you can exchange information about routers and networks through link state advertisements packets. You can use what's called intermediate system to intermediate system. It's Cisco's proprietary enhanced interior gateway or routing protocol, or we can call it EIGRP. Back in the days when RIP was dominant, there was a huge outcry for an improved RIP, and that's where it came from. Okay, so I just put these on the board to familiarize yourself. You absolutely, positively need to master these because they will be on the test. So you'll need to know what they stand for, how they're different, what kind of systems are they connecting. So I like to think as RIP and BGP is kind of how things started off, right? And then they kind of expanded from there. So RIP had a lot of problems. Okay, it got outdated, and how we route and costs and metrics and values and all that really is going to depend on what technology you're using. Okay, we also need to talk about route redistribution and administrative distance. That's used to determine which route is the most reliable. You'll see this featured also called route preference. So it's always improving and expanding, right? Okay, well, we can't talk about routing without getting physical. So you need a way to connect to your router. Simply taking it out of the box and putting it on a rack with other equipment isn't good enough. When you take a router or switch out of the box, it doesn't do very much. You need to connect to it via console cable. The classic Cisco console cable, more commonly called a rollover or a Yoast cable, kind of looks like that. And you would put the other end of a DB9 connection to a DB9 receiver to a USB and then to a computer. Or I suppose if you have some interface that takes that. But yeah, this is pretty common to see in the world of networking. A lot of equipment like switches and routers and firewalls, they have a console cable that looks like that, and you have to use a console Yoast, depending on what kind of equipment you're using and proprietary. But it'll look something like that. Here's an example configuration of what PuTTY looks like and what you'll need to use. Okay, pretty standard is to specify what COM port you need. So depending on where you're plugging that in, it'll be COM1, COM2, COM3, COM4. So you'll have to look at your devices on your computer to know. You'll have to know the different speed or baud rates. 9600 is pretty common. Trying to think what else, like 115200 is one that I've used. Okay, 8 bits of data. Stop bits are usually 1 or 0, and then these are usually set to off also. And let's kind of take a look here and see what this Cisco device is telling us. Okay, it's undergoing a cold start, so it's just turning on. Yep, and you can see the output. Every little line, every detail, as it's booting up, it gives you messages, it's debugging, and this is what it looks like to be essentially a network administrator, just programming switches and firewalls all day. Okay, so you need to use different network management software, and there's a lot of options for you to try. One that's really common is OpenNMS. And that will let you monitor things in detail. And even if you have some sort of system that already is monitoring, it's not enough. You may need to expand it, you may need to change it, you may need to have some sort of alert that works differently. So it's a big job to administer all of these systems and alerts. Okay, so let's go through setting up the internet. Like day one, you're opening the office. Okay, step one is to set up your WAN side or wide area network. So the ISP has said, hey, our signal's live. Is our modem on? Do you see a light? And then you can specify if you want it to be DHCP. You can specify if you want it to be IP. Most likely your ISP is going to give you some IP address information and you'll punch it in kind of looking like that. You can specify the LAN side. So now you have the connection to the world, you have the wide area network, but what about your local area network? You're protected. You don't normally talk to the outside world. So these computers are in their little private zone and they're protected from your firewall and all of these rules, and things cannot route to it. It's impossible. So your local area network will probably look like that. We have a class C address, 192.168, blah, blah, blah. Okay, you can go through your routing tables and look through it. Oftentimes there's like a bad route or something that gets missed. Okay, And the last thing I'm going to talk about is MTUs, or maximum transmission unit. So you can specify how much information or how long it will keep going and sending out data. Congratulations, you made it to the end. It's the pop quiz. Okay, where would a packet for 64.165.5.34 be sent? Do we have a default route? Yes, we do. So that's 000. So this is our gateway. We know that's our gateway. Okay, so is that local? Is that local? Yeah, that's on our network, right? Okay, so here, 34, is that inside this subnet mask? 34, yes it is, and that's going out the WAN, so that would go out to the internet. So that also means that your private network or local area network is like some sort of 10 dot address. Cool. Next question. What happens if you ping 127.254.254.254? Well, pause the video and do it now. Go to a command prompt and ping it. What do you get? Come back. Okay, are you back? Why did that work? Well, we talked about the royal flush here. When you do all of these, that'll route every address available from this network ID, from this network mask, out to that interface. So it'll respond to the loopback. The loopback is always the 127.0.0.1. Okay, last question. Give an example of IGP and EGP. Okay, so you need to know these different border gateway protocols, right? So we talked about AS, or autonomous systems, and the policies they have. Originally it was a 16-bit number, but it became 32-bit numbers. So these AS, or autonomous systems, they use an exterior gateway protocol known as a EGP, BGP, EGP. Yep. And they can communicate with other protocols as well, like an interior gateway protocol. So we can see examples here, right? IGP, we can use open shortest path first. We talked about Cisco's variation of RIP. And yeah, like older one, we can use RIP too. So all kinds of different routing technologies interconnecting, working together. You can design things to work. It can be as simple or complex as you want it to be. Thank you for watching. Have a great night.